This is the last lecture from Chapter 13, and this lecture is all about reaction mechanisms. What is a mechanism? A mechanism is the detailed route that reactants follow to make it to products. So just like if you go to the store, you can take there are different ways you can get there. You can take different streets. Same thing with reactants. They follow a particular pathway. And the overall reaction equation that you're used to balancing and using for stoichiometry and chemistry doesn't tell you anything about the detailed step-by-step mechanism. So that's what this unit is about, or this lecture. So the book definition for mechanism is that it is a sequence of molecular level steps, which we call elementary steps. That's important vocabulary, elementary steps, that tell us how we get to the product. And again, the balanced reaction that you're used to dealing with, A plus B gives C, tells you nothing about the mechanism. The nice thing about the elementary steps is each elementary step can give us important information about the rate of a reaction. Molecularity is another vocabulary word, and that tells you how many reactants are involved in one particular elementary step. That'll make more sense as we go on. Let's talk about molecularity first. As I said in the last slide, molecularity is how many molecules are involved in one particular elementary step. So just take a minute, look down here. If this is an elementary step, one detailed step in a series of mechanistic steps, its molecularity would be 2. In other words, it'd be called bimolecular. Okay. On the other hand, this particular elementary step has 3 molecules involved, so it would have a molecularity of 3. What I think is especially cool about elementary steps is that you can write a rate law for an elementary step directly from the equation for the elementary step. So if we had an overall reaction equation that looked like this, if you wrote the rate law, that you would have no idea what the order with respect to A was from the overall equation. But if it's an elementary step, and they have to specify, you'd be talking about mechanisms in elementary step, you can write the rate law for that elementary step directly from the elementary step. So if it's a bimolecular elementary reaction, then the exponent for the order is 2. If the molecularity is 3, then you write an order of 3. So we'll do more with that, but that is really handy. So let's look at a particular reaction and its elementary step. This would be the overall reaction between nitrogen monoxide and molecular oxygen to give nitrogen dioxide. That's an oxidation reaction. And so scientists through studying have found that the mechanism of this shows that it actually occurs in 2 elementary steps. The first step is bimolecular, of course, because it involves, my stylus has stopped working. It involves 2 molecules. They can be the same or different. No. And the second step is also bimolecular because it involves 2 molecules. So thinking about that same reaction again, let's go ahead and write the rate laws for the individual elementary steps. So step 1 for this reaction was this. Okay, so if I write it out kind of longhand, it would look like this. Okay, and so the rate law, remember from an elementary step, you can write directly. So it's some rate constant times the reactants raised to the power of how many there are. Step 2, again, these are mechanistic steps, so that's the only time you can write a rate law directly from an equation. So the rate law for this second elementary step, some rate constant, we'll give it a different subscript to show it's for a different elementary step, times the concentration of all the reactants. Okay, there are only one of each of these, so the order of each is 1. So now, great, we have 2 elementary steps. We have the rate law for each of the 2 elementary steps. What is the rate law for the overall reaction? So that takes a little bit more thought and work. So let me give you a picture to kind of set the stage. So if you have multiple steps in a reaction, and each step in this picture is kind of a cool picture, is represented by a funnel, and each funnel has its own rate at which things pass through, which of these funnels is going to determine the overall rate at which the liquid gets into the ultimate container? Okay, which of these steps is going to be more important? It depends on the slowest step. Okay, the slowest step, just like the weakest link, is the one that determines the rate for the entire reaction. In kinetics, we call that the rate determining step. It is always the slowest step. So if you look back at our funnel picture, if you change the size, which stands for rate, of one of these steps, okay, it's going to back up. That's the slow step, okay? And so the entire rate of reaction is going to be determined by this slow step. However, whatever the rate of the slow step is the rate of the entire reaction. And so it works the same with elementary steps. You have to identify which of the elementary steps in a mechanism is the slowest one, and that determines the rate of the entire reaction. So let's do a couple practice problems. So just to remind you of the 2 steps in this reaction we're talking about, I like to call it the no-no reaction. Going here. So which of these 2 steps is slower? How do we determine that? You have to be told, by the way. There's nothing you can specifically do. It gets determined experimentally. All right, so let's imagine one by one that each of the steps is slowest. So let's first imagine that the first step is the rate determining or the slowest step, okay? The rate law for the first step in the mechanism was this, okay? So if that's the rate of the slowest step, and it's the first step in the reaction, that equals the rate law. No problem. So if I were you, I'd make a note right now that if the first step in a mechanism is the slowest step, that's the rate law, you're done, easy. It's not so easy if a step other than the first step is the slower one. So because you have to do some math and some substitution. So this is where you really need to pay attention and make sure you understand what I'm saying. So if the first step in a mechanism is faster than the others and a subsequent step is the slowest one, let's look at this reaction in particular. Here is the rate for that second slower step. What would be wrong with calling this the rate law? I'll tell you right now, we can't. But see if you can look at this rate law expression and then look at the reaction that we're talking about, the overall reaction, and see if you can figure out, you probably can at this point, but I don't have enough information. What would be wrong with using this the rate law? Well, I'll tell you right now, and that is rate laws must be expressed in terms of reactants, okay? So is this rate law, oh, my stylus is really croaking here. So is this rate law expressed in terms of reactants? Well, let's see, oxygen is a reactant. What on earth is N2O2? Where did that come from? It's not a reactant. So this is impractical as a rate law. Chemists, when they get a rate law, have to be able to follow the changing concentration of the reactants. They look at N2O2 and they're like, what is this? How do we follow the concentration of this? It's just too complex. So if you have something in the rate law that is not a reactant, in this case this is an intermediate, and we will talk more about intermediates in a minute, rate laws cannot be expressed in terms of intermediates. They must all be reactants. So you need to find some way to express the concentration of this intermediate in terms of reactants. And that's where it gets slightly complicated. So I'm going to show you that on the next slide. So here's what you do if the first step in a mechanism is fast and not rate determining. So here's the first fast step that we've been talking about in the last few slides. So if it's an elementary step, so you can write the rate law directly from the elementary step. So here is the rate law for the forward reaction. But now I want you to do something a little bit different. You're going to be doing a lot more of this in the last chapter. I want you to look at the reverse reaction. I've mentioned before that once a reaction gets going and you have a chance to build up product, that most reactions can go in the reverse direction. In other words, product can reform reactant. So I want you to envision this reverse reaction. So let me go ahead and write out, you may be able to look at it backwards, but I'm going to go ahead and write out what the reverse reaction would look like. So we're going to take the product and we're going to show that it can go back to form reactant. This is the reverse reaction. So just like any mechanistic step, forward or reverse, you can write a rate law. So the rate law for the reverse reaction, and I'm expressing that it's reverse just using this negative sign, is equal to some rate constant and times the reactant, which in this case is formerly the product, N2O2. So now you have a rate law expression for the forward reaction and a rate law expression for the reverse reaction. Because, and you may not have learned this, but it's very, very, very important. It's actually also a lead into chapter 14, our next chapter. But because the rates at equilibrium are equal, so that what that means is the rate of the forward reaction is equal to the rate of the reverse reaction. That is the definition of equilibrium. And because this first step in the mechanism is fast, we're going to make the assumption that equilibrium is established quickly. Okay? We're going to assume that the first fast step is at equilibrium almost right away. So what that means is we can set the rate of the forward reaction equal to the rate of the reverse reaction because we're assuming equilibrium. Doing so allows us to make a substitution and get rid of the intermediate. Remember, the N2O2 is an intermediate. It's not a reactant, isn't a product. Definition of intermediate is something that gets formed in the middle of a reaction and also gets consumed in the middle of a reaction. So it doesn't show up as either a product or a reactant. So now that we have the intermediate in terms of something else, namely a reactant, we can substitute back into our rate law. So I'm going to rearrange this equilibrium expression so that I have something else to plug in for N2O2, the intermediate. So back to the original rate law we got for the rate determining step being the second step. Anytime I see N2O2 in that rate law, I'm going to cross it out and instead put in this expression. So here we go. Here was the original rate law that we got when we assumed that step 1 was fast and step 2 was rate determining. Remember that we want to get rid of the N2O2 because it's an intermediate. So based on what I just said on the last slide, every time I see N2O2, I'm going to plug in what we found we could substitute for. And that was concentration of N2O2 equals K1 over K minus 1 times the concentration of NO. All right, so that's where this came from. We just simply crossed out the N2O2 and plugged it in with its replacement. And now what gets kind of messy are all these different rate constant. And this overall reaction is going to have just one single rate constant of its own. So we're just going to cross out all these random rate constant and give it some new K value that represents all of them combined. So here we are. Now we have a substituted rate law for the overall reaction. And if you remember that, the overall reaction that we're talking about is this. And now we have a rate law, an overall rate law for the equation that we can use. And it's in terms of, oops, I left off O2. It's in terms of reactants only. So here's one for you to practice on. This gets kind of complicated, so you may want to spend a little bit of extra time, more than ordinary, on these substitution reactions. So I want you to look at a new reaction and look at the experimentally determined rate law and identify, this is just a different way of asking a similar question, which of these two mechanistic steps is the rate limiting step. Now the hint I'll give you is remember that the rate limiting step, rate determining step, is the one that determines the rate or the rate law of the reaction. So see if you can put me on pause and figure out which of these two steps is the rate determining step, and then I'll go over it on the next slide. And that is it for the lecture on mechanisms. I feel like I probably should have given many more examples in this because mechanisms can trip people up. So what I want to ask you to do is make sure you go into the content section of D2L in the folder that says in-class worksheets, and I want you should be at least looking at all those worksheets, preferably working a few problems off each. But I want you to definitely pull out the worksheet on solving mechanisms because there are quite a few more twists that can be asked and questions on these, and I know from past experience that you're going to need to practice. So I would like you to work on that worksheet. But guess what? We are done with Chapter 13. Be prepared for an in-class quiz over this, and we will start, when we finish this, we'll start in Chapter 14, which is equilibrium.